Imagine building a groundbreaking, state-of-the-art piece of hardware. Like you are sitting right there at a workbench.
Just staring at the board.
Exactly.
Yeah.
The soldering iron is just starting to cool off, and you have just finished assembling a custom 8086 microprocessor card.
Designed specifically for an S100 bus.
Yeah, exactly. So you plug this board into the backplane, you power it up, and the diagnostic lights blink in perfect sequence.
It actually works.
It works. The hardware is completely flawless. And then, as the adrenaline sort of fades, you realize something genuinely terrifying.
Oh yeah, the missing piece.
There is literally no operating system on the market that can run this hardware.
Not at all.
You've constructed this incredibly powerful engine, and there are absolutely no roads to drive it on. So what do?
I mean, if you were approaching this from a modern, sensible engineering perspective, you probably just halt production. You wait for the software ecosystem to catch up. Or you try to partner with an established software vendor to build the necessary layers. But if you are the team at Seattle Computer Products in the late 1970s, operating in the absolute wild west of early microcomputing, you do not have the luxury of waiting.
You really don't.
You just roll up your sleeves and write the operating system yourself from scratch.
Which is exactly the premise of today's deep dive. We are looking really closely at a foundational text in computing history. It's called An Inside Look at MS-DOS, authored by Tim Paterson.
The original architect of the operating system.
Yeah, at Seattle Computer Products. We are going to completely deconstruct the heavily constrained design decisions behind the earliest versions of MS-DOS.
It's a fascinating mission for this deep dive.
It really is. Our goal today is to understand the exact bare metal mechanics of how these early builders squeezed maximum speed and efficiency out of literal kilobytes of memory.
Literal kilobytes.
And more importantly, we are going to look at what we, as modern engineers working with practically infinite resources, can learn from those brutal, unforgiving constraints.
To really grasp the magnitude of what Paterson was building, we need to completely reset our expectations about development environments.
Yeah, absolutely.
It is very easy to look back at the late 70s and just assume things were, a bit slower.
Just a bit clunkier.
Right. But we are not just talking about slower compile times or a lack of syntax highlighting. We are talking about a fundamentally different physical reality of programming. Paterson's primary development tools consisted of an assembler that was running on an older 8-bit Z80 chip.
And a primitive hardware monitor and debugger.
Exactly.
And we really have to clarify what a monitor and debugger meant in that era. It wasn't a software application running in a nice little window.
Not at all.
It was a piece of low-level machine code that allowed you to inspect memory addresses and registers directly.
Right. And here is the constraint that completely reframes the engineering achievement for me. That entire debugger had to fit inside a tiny 2-kilobyte EEPROM.
2 kilobytes?
2 kilobytes of erasable, programmable, read-only memory.
Yeah.
For context, if you wanted to change a line of code in that debugger, you couldn't just hit backspace and recompile.
No, you had to physically remove the chip.
You had to physically pull the EEPROM chip from the motherboard, place it under an intense ultraviolet light for 20 minutes to erase it, and then use a dedicated piece of hardware to burn the new machine code back onto the silicon.
Which is just wild to think about today.
2 kilobytes is smaller than the metadata overhead of a blank text document today.
Yeah.
That was the entirety of the tooling available to build what would become the most dominant operating system of the personal computing era.
It is the ultimate builder constraint. You have a massive industry-defining goal and almost zero infrastructural resources. But before we even get into the raw code, the registers, and the bitwise math, we have to talk about the primary obstacle they faced, which was not actually a technical problem.
It was an adoption problem.
Exactly. You can build the most elegant, perfectly optimized, mathematically pure system in the world, but if no one is willing to write software for it, it is essentially useless.
This touches on something we still see constantly today, especially when you're assessing new AI frameworks or hardware accelerators. The ecosystem is everything.
Everything.
At that specific time, the computing ecosystem was completely monopolized by an operating system called CP/M80. If you were an independent software vendor writing an application,
Like a word processor or a spreadsheet.
right, a database, whatever, you wrote it for CP/M, the market inertia was absolute. If you introduce a brand new, unproven operating system running on a brand new 16-bit hardware architecture, you are asking developers to take a massive financial and technical risk.
It is the classic platform economics trap.
Yeah, you need an installed user base to attract the developers, but you need the developers to build the applications that attract the user base.
So the engineering strategy Paterson employed was brilliant in its pure pragmatism. The primary design requirement of MS-DOS from the very first line of code was absolute CPM80 translation compatibility.
The architecture was specifically designed to be a bridge.
Exactly. Patterson looked at Intel's published translation rules, the guidelines for how to mechanically translate old 8-bit 8080 or Z80 assembly code into the new 16-bit 8AA6 assembly code,
And he followed them strictly.
to the absolute letter. The pitch to the software developers was highly targeted. If you have an existing program written for the old standard, you can run it through a mechanical translator, and it will execute perfectly under this new MS-DOS environment.
Often on the very first compilation attempt.
Right. They didn't ask developers to rewrite their code, they gave them a translation layer.
But wait, even with that translation bridge, the historical reality check is actually quite harsh.
Oh yeah, it wasn't an instant success. The industry didn't just immediately embrace MS-DOS. In fact, most early developers completely ignored it. They assumed that Digital Research, the company behind the dominant CPM standard, was going to release CPM86, and that it would naturally become the undisputed 16-bit standard. The inertia was just that strong. The market inertia was so powerful that a superior technical bridge wasn't enough to overcome it on its own. It wasn't until IBM made the monumental decision to step into the personal computing market and selected MS-DOS as the primary operating system for the IBM PC that the entire industry was forced to pivot.
Which provides a massive, enduring takeaway for anyone building systems today.
Yeah, what's the lesson there?
Sometimes your technical architecture has to proactively compensate for market inertia. You cannot engineer in a vacuum, assuming the best technology will organically win.
You have to build for reality.
You have to engineer for the reality of human behavior, legacy code bases, and existing market monopolies. MS-DOS survived its vulnerable early months solely because its architecture lowered the friction of adoption to near zero. Okay, let's transition into the actual internal architecture of the system, because the way they structured the boundaries between the hardware and the software is fascinating.
It's a classic abstraction model.
It's fundamentally a layer cake of abstraction. To make this tangible, I like to visualize it using a restaurant analogy.
Okay, let's break down that layer cake using a restaurant. We can unpack the 3 core files that actually make up MS-DOS, starting from the very bottom, closest to the physical metal, IOSYS.
In our restaurant analogy, IOSYS represents the physical kitchen appliances, the raw plumbing, and the electrical wiring.
The messy stuff.
Exactly. It is entirely, unabashedly hardware dependent. You have to remember that in the early days of microcomputers, there was absolutely no standardization. None.
Every single manufacturer was doing their own thing.
Every single hardware manufacturer utilized different custom disk drive controllers, different physical sector sizes on the magnetic media, different keyboard matrix layouts.
Different serial communication chips.
Right, so IOSYS was actually written and customized by the hardware manufacturers themselves, not by Microsoft.
Because they knew their own hardware.
The hardware vendors are the only ones who know the precise voltage timings required to step their specific magnetic read and write head across the disk. IOSYS handles the grittiest low-level work. It is responsible for outputting a single electrical pulse to represent a byte, or reading a raw physical magnetic sector off a spinning platter.
It is the raw mechanics, deeply tethered to the physical world. But application developers do not want to worry about voltage timings.
God, no.
So sitting directly on top of that raw plumbing, you have the hidden core of the operating system, MS-DOS.
MS-DOS is the head chef or the general manager of the restaurant. Its primary characteristic is that it is completely device independent.
It doesn't care about the hardware.
When a high-level application, say a word processor, wants to save a document, it absolutely does not talk to the hardware. It talks to MS-DOS SY.
It makes a request.
It sends a highly abstracted request, effectively saying, here is a chunk of data. Please append it to this specific file. MS-DOS takes that high-level abstract concept of a file and translates it into the specific low-level operational instructions that IOSYS requires.
And that's why the system is portable.
Because it operates purely in the realm of logical abstraction, this specific file, MS-DOS, is nearly identical across every single MS-DOS machine in the world. regardless of whether it is running on an IBM PC, a Tandy, or a custom S100 system.
This separation of concerns implemented here is vital for the survival of the platform. By completely abstracting the messy, chaotic physical reality away from the core logic, you allow software developers to write an application once and trust that it will run on any hardware that has an iOS implementation.
Right.
But the end user, the human being typing on the keyboard, never directly interacts with the head chef. The user interacts exclusively with the third layer of the cake, command.com.
Command.com is the front desk. It is the menu, the waiter, and the maitre d'. It is the standard user interface. Its job is to accept human-readable commands from the console prompt, interpret what the user is actually trying to accomplish, and then execute the correct sequence of system calls to the head chef.
But there is a crucial, deeply technical detail about command.com that often gets glossed over.
Which is?
It is entirely responsible for setting up the fundamental error trapping for the entire system.
Wait, really?
Things like catching a catastrophic hard disk read failure or intercepting a Control-C abort command when the user realizes they're stuck in an infinite loop.
We need to pause on that because it highlights a shocking architectural constraint. It is responsible for error trapping because MS-DOS-Y, our sophisticated head chef, provides absolutely zero default error handling natively.
Zero.
If a disk read fails, the OS kernel simply traps through a hardware vector that it assumes has been previously configured. Wait, let me make sure I'm getting this entirely straight. You were saying the core operating system kernel just throws its hands up when a physical error occurs and blindly jumps to a memory address, just assuming something else has built a safety net.
Precisely. The kernel delegates the failure state. If command.com, or whatever alternative command processor you are using, fails to properly set that specific trap vector in memory and provide a robust response routine, the entire system simply crashes.
It just dies.
The instruction pointer wanders off into garbage memory, and the machine halts. The core OS assumes the application layer has prepared the emergency exits.
Which naturally brings us to one of the most aggressive, almost hostile architectural optimizations in the entire text.
This is my favorite part.
Because available RAM was so unbelievably scarce, we are talking about systems with maybe 64 kilobytes of total memory. Command.com utilizes a highly unorthodox split memory model. It actually cleaves itself into two completely separate physical pieces just to conserve a few thousand bytes.
The transient versus resident split. This is where you see the sheer necessity of bare metal engineering. Let's look at how this mechanism actually functions in RAM.
Walk me through it.
The first piece of the program is the resident section. This code is loaded into low memory, residing right above the core MS-DOS kernel itself. It contains the absolute critical infrastructure that can never, ever be unloaded.
Like the error trapping vectors we just discussed.
Exactly. The vectors, the logic for processing batch files, and the specialized routines required to resurrect the rest of the program. Once the resident section is loaded into low memory, it stays put until the machine is physically powered down.
But the second piece, the transient section, is where the engineering gets truly wild.
It really does.
This section contains the code that actually interprets the user commands, the dir, copy, and format commands. And it lives all the way up at the very highest end of available system memory.
But the critical operative word here is transient.
It is considered expendable.
Highly expendable. If a user launches a third-party application that is extremely memory hungry, MS-DOS does not throw an out-of-memory error.
It does something much stranger.
Instead, it allows that third-party application to literally trample right over the transient section of the command processor.
It just overwrites it.
The application is given permission to pave over the operating system's own user interface to secure the RAM it needs to function.
To put that in perspective, imagine your modern operating system quietly terminating the desktop rendering engine just so you can open one more tab in your web browser.
That is a great way to think about it.
When that memory-hungry application eventually finishes its task and closes, the resident section down in low memory wakes up. It calculates a checksum, realizes its upper transient half has been completely destroyed by the application, and quietly reaches out to the physical disk to reload the transient section back into high memory from scratch.
It repairs itself.
It is an operating system that intentionally allows itself to be partially corrupted, to squeeze out an extra 5 or 6 kilobytes of workspace for the user, and then heals itself afterward.
Viewing this through a modern lens, it is completely antithetical to how we design systems today. Modern operating systems are fiercely protective of their memory space.
Absolutely. We use hardware-enforced rings of privilege, virtual memory paging, strict process isolation.
If a user application tries to write into the operating system's memory space today, the CPU generates a segmentation fault, and the OS violently terminates the application.
Right, it kills the app to save the OS.
But in 1980, the OS politely stepped aside and offered up its own vital organs just to keep the application running. It forces you to respect the sheer ingenuity born of absolute scarcity.
Okay, so command.com obviously provided a built-in set of instructions, but it was designed to be easily extensible.
Right.
You were not restricted to the internal commands. You could execute external programs seamlessly. The architectural text outlines 3 very specific executable extensions that the system recognized natively.
The .com file, the .exe file, and the .bat file.
Let's look deeply at the .com files first, because from a purely structural standpoint, they are a masterclass in minimalism.
They are so simple.
A .com file is a pure, raw, binary program. If you look at it in a hex editor, there is no file header, there is no metadata, there is no signature.
It's just code.
The very first byte of the file is the very first machine instruction to be executed by the CPU. But this absolute simplicity comes with a very rigid, unbreakable constraint. The entire program must fit perfectly within one single 64-kilobyte memory segment.
Code and data.
Both the executable instruction logic and all the data it intends to manipulate must reside in that single contiguous 64K block.
And the reason for that 64K limit is tied directly to the architecture of the 8086 processor, which relies heavily on segment registers. Because a .com file contains no relocation data whatsoever, the operating system can scoop up that raw binary, drop it into literally any available 64K memory segment in RAM, set the instruction pointer to the beginning of that segment, and it just runs flawlessly.
No parsing headers.
It requires zero processing overhead at load time. It is as close to raw, unadulterated machine execution as you can possibly get within an operating system environment.
It is highly elegant, but it is also severely limiting. If you are trying to write a complex database application, 64 kilobytes for both code and data is going to become a suffocating bottleneck almost immediately.
You hit that wall fast.
So what happens when you need an application that spans multiple segments? That is where the .exe file format is introduced. Unlike the barebones .com file, an .exe file begins with a highly structured, specialized header.
And the primary purpose of this header is to contain a massive table of relocation information.
We need to explain exactly why that relocation table is necessary.
Right, so when you are writing a massive program in C or assembly and compiling a binary that will span 3 or 4 different 64K memory segments, your compiler has a fundamental problem.
It doesn't know where it's going to live.
The compiler has no idea exactly where in physical RAM the operating system is going to eventually place this program. The physical addresses are completely unknown at compile time.
Right. The program might be loaded at memory address 10,000 today, but tomorrow, if the user has a memory-resident program running, it might be forced to load at address 50,000.
Exactly.
So if your code in segment A needs to jump to a specific function located in segment B, the compiler cannot hard-code the physical memory address for that jump. Instead, the compiler leaves a placeholder and records the location of that placeholder in the .exe relocation header.
And then the OS takes over.
When MS-DOS loads the .exe file into memory, it doesn't just copy the bytes. It dynamically reads that entire header, iterates through every single entry in the relocation table, and mathematically adjusts all of those memory pointers on the fly.
Adding the base offset of the physical load segment to the placeholders.
It is performing dynamic, real-time memory translation right at the moment of execution.
Which is a tremendous amount of computational overhead for a 1980s processor just to start a program.
But it completely breaks the 64K memory barrier, allowing software to grow to the physical limits of the installed RAM.
Finally, alongside the binaries, you have the simple .bat files, which are nothing more than standard ASCII text files containing a sequence of commands that command.com reads and executes one line at a time.
It is the primitive ancestor of modern shell scripting.
But I want to pivot back to something we touched on when we discussed the iOS-YS plumbing layer, because it introduces what might be the single most important conceptual leap in the entire architecture.
The abstraction of the disk media.
Ah, yes, the spinning rust.
The spinning rust.
If you take a physical 8-inch or 5.25-inch floppy disk, or even a heavy Winchester hard drive from that era, and look at how it operates mechanically, it is a nightmare of moving parts.
Total nightmare.
The magnetic surface is divided into concentric circular tracks radiating outward from the center spindle. Each of those circular tracks is further sliced up into individual physical sectors.
And to read data.
To read a specific piece of data, the disk controller hardware has to physically step a mechanical read-write head across the platter to the correct track, and then it has to sit there and wait for the spinning disk to physically rotate the correct sector under the magnetic head.
And from a software engineering perspective, forcing an application to understand and navigate that two-dimensional coordinate system, specifying track 14, sector 7, is a complete architectural dead end.
It doesn't scale.
Especially because every single hardware manufacturer had wildly different geometries.
Yeah.
Some disks had 40 tracks, some had 80, some had 8 sectors per track, some had 15.
If MS-DOS forced applications to hard-code their disk access based on physical tracks and sectors, your application would be locked to one specific brand of disk drive forever.
To solve this, Paterson introduced a brilliant, sweeping abstraction layer. MS-DOS completely and utterly ignores the physical mechanical reality of the disk drive.
It just pretends it doesn't exist.
It strips away the concept of tracks, heads, and physical rotation entirely. Instead, the operating system views every single disk as a simple, continuous, one-dimensional mathematical array of what it calls logical sectors.
Just a flat list.
It just assigns them sequential integer numbers, starting from logical sector 0 and counting up to logical sector n-1.
Let's map that out physically to see how the abstraction holds up. Logical sector 0 is defined as the very first physical sector on the absolute outermost track of the disk.
Right.
The OS counts sequentially around that outer track. When it completes the circle, it automatically increments the track number, drops inward to the next concentric ring, and continues counting sequentially, spiraling all the way inward to the very last sector on the innermost track.
It is a complete paradigm shift. You are moving from a complex, mechanically dependent 2D geographical coordinate system to a simple, perfectly flat list of integer addresses.
An application program never has to ask the disk to seek to track 14.
It just sends a generic request to ms.or.sys.
Please retrieve the data located in logical sector 450.
The application is blissfully ignorant of where that data physically resides.
It is the IOSYS layer, the hardware-specific plumbing written by the drive manufacturer, that takes that integer 450, runs it through a geometry algorithm, and translates it back into the physical instruction to move the head to track 14, sector 7.
This exact abstraction is the hidden mechanism that allows a user to take a floppy disk out of an IBM machine, carry it across the room, plug it into a completely different machine manufactured by Tandy or Compaq with a totally different physical drive mechanism, and still read the data flawlessly.
By reducing the disk to a flat mathematical array, they made the file system completely hardware agnostic.
So let's take a magnifying glass and look at how that flat, one-dimensional array of logical sectors is actually divided and utilized. The source text gives us the exact sector-by-sector layout for a standard 8-inch, single-sided, single-density floppy disk format.
All right, let's walk through the exact topography of the disk. Logical sector 0, the absolute first block of data on the disk, is strictly reserved for the bootstrap loader.
When you power on the computer, the hardware is incredibly dumb.
It really is.
It only knows enough to read the very first sector of the disk into memory and execute whatever code it finds there.
So sector 0 contains a tiny, dead simple, highly optimized assembly routine whose sole purpose in life is to wake the machine up, initialize the hardware, and provide the instructions on how to locate and load the rest of the MS-DOS kernel from the disk.
Immediately following the boot sector, occupying logical sectors 1 through 6, you have the very first copy of the FAT, the File Allocation Table.
And directly following that, occupying logical sectors 7 through 12, you have a complete identical second copy of the File Allocation Table.
I have to pause you there. Why allocate 6 precious sectors to an exact duplicate right next to the original?
Pure paranoia regarding data integrity.
Paranoia.
Floppy disks in the late 1970s and early 1980s were notoriously infuriatingly unreliable media. The magnetic coating could easily flake off. A speck of dust, a fingerprint, or a stray magnetic field from a nearby telephone could instantly corrupt a sector.
And if that sector is the FAT,
The FAT is the master map of the entire file system. If a speck of dust corrupts the FAT, the actual file data might still be perfectly intact on the disk, but the operating system has completely lost the map of how to find it or piece it together.
the disk becomes a useless jumble of bytes.
You lose everything. So they intentionally dedicate space to a backup copy sitting side by side. If the OS detects a read error on FAT1, it silently falls back and reconstructs the data from FAT2.
Okay, so after the master maps occupying logical sectors 13 through 29, you find the directory structure.
This is the central repository where the human-readable metadata lives.
And the directory is not a free-form test file. It is a rigid, highly structured database. Every single file on the disk is allocated exactly one 32-byte entry in this directory area.
Those 32 bytes are packed incredibly tight.
They hold the 8-character file name, the 3-character file extension, a byte for system attributes like whether the file is read-only or hidden,
The exact time and date the file was last modified.
the precise file size down to the exact byte, and finally, a critical integer pointer. That pointer tells the OS exactly where to look in the FAT to find the very first physical chunk of the file's data.
And everything sitting after the directory, starting at logical sector 30 and continuing all the way to the end of the disk at logical sector 2001, is the data area.
This is where your actual word processing documents and binary applications are stored.
But here is the critical optimization. MS-DOS does not manage this massive data area sector by single sector. Tracking thousands of individual sectors would create an impossibly large map.
Instead, it groups the logical sectors together into contiguous blocks called allocation units.
Which we often refer to as clusters. And this specific grouping mechanism brings us to one of the most intense foundational engineering debates in early operating system design.
The great fragmentation trade-off. Okay, we need to unpack this carefully because understanding fragmentation is the key to understanding how disk storage actually functions under the hood.
What?
There are two entirely different types of fragmentation that an OS architect has to worry about: external fragmentation and internal fragmentation.
Let's clearly define external fragmentation first. The easiest way to visualize this is to imagine a massive, crowded parking lot.
Okay, a parking lot.
Over the course of a day, cars are constantly arriving, parking, and leaving at random times. Eventually, the parking lot is mostly full, but you end up with single, empty parking spaces scattered randomly all over the lot.
Right.
Now, imagine a massive articulated bus pulls up to the gate. The bus requires 5 empty parking spaces in a row to park. Even if there are 20 empty spaces total in the lot, the bus cannot park because there are not 5 contiguous spaces next to each other.
That is external fragmentation.
Exactly. You have massive gaps of unallocated free space, but the gaps are too small and scattered to be useful for storing a large continuous file.
But MS-DOS completely and elegantly eliminates external fragmentation. It permanently solves the parking lot problem. Unlike more primitive, rigid file systems like the UCSDP system, which absolutely required a file to be written in one continuous block, MS-DOS does not care about contiguity.
Not at all.
An MS-DOS file can be chopped up into tiny pieces and stored in those single, isolated, empty parking spaces scattered randomly across the entire surface of the disk.
A file allocation table serves as the master tracking system to remember where all the individual pieces were hidden.
So, because the OS can utilize any free space anywhere, external fragmentation essentially drops to 0.
However, and this is the crux of the engineering debate, by eliminating external fragmentation, they traded it for a massive, unavoidable headache with internal fragmentation.
The wasted space inside the box.
Yes, internal fragmentation is the wasted, unusable space trapped at the very end of an allocation unit. Let's make this concrete. Let's say the OS designers decide that an allocation unit will consist of 4 sectors, which equates to exactly 512 bytes of storage. If a user writes a tiny configuration file that is exactly 1 byte long, MS-DOS cannot just dedicate 1 byte. The smallest unit of storage it can track is an allocation unit. So it dedicates an entire 512-byte block to hold that single byte of data.
You are instantly wasting 511 bytes of precious disk space.
To stick with the real-world analogies, it is the equivalent of renting an entire massive industrial warehouse just to store a single shoebox.
And the statistical reality is brutal.
Okay.
Let's assume you have a file that spans dozens of allocation units. The final unit is rarely going to be perfectly full.
Right, mathematically speaking.
Statistically, on average, the last allocation unit of any file on the disk is going to be exactly half full. So you are guaranteeing that you will waste half of an allocation unit for every single individual file stored on your disk.
It adds up fast.
So here's my yeah but moment as an observer, put on my systems architecture hat. If internal fragmentation wastes all this precious space on a small floppy disk, the logical solution seems obvious.
That's the obvious solution.
Why not just configure the allocation unit to be exactly 1 sector long, 128 bytes? Make the warehouse the size of a shoebox. That minimizes the internal waste to almost nothing. Why accept the waste?
It is a totally valid, intuitive question, and it is a debate that system engineers fought over constantly. But let's actually do the mathematical reality check, because when you run the numbers, the scale of the overhead becomes staggering.
Show me the math.
Let's look at that standard 8-inch disk format the text outlines. It contains exactly 2002 sectors, and each sector holds 128 bytes.
Okay, I have the parameters.
If you, as the architect, decide to make your allocation unit exactly one sector long to perfectly minimize internal waste, you now have 2,000 individual discrete allocation units that the operating system has to track in its database.
In the FAT.
Right. To track them, you must populate the file allocation table. The architectural math of MS-DOS dictates that the FAT requires 1.5 bytes of memory for every single tracked unit. So 2,000 units multiplied by 1.5 bytes means your FAT array is now 3,000 bytes long.
Which, if we divide by 128 bytes per sector, means that FAT takes up nearly 24 whole sectors on the disk.
Exactly. And remember the paranoia rule we discussed earlier?
Oh, right. We require 2 completely independent copies of the FAT for redundancy.
So now you are permanently dedicating almost 48 sectors of your disk just to store the metadata map of the disk.
Okay, I see the overhead growing.
Okay.
But how does that 48-sector penalty compare to the space we would have lost to fragmentation waste if we use larger units?
Let's run a highly realistic simulation. Let's assume the average file size you are saving in 1980 is 16 kilobytes.
Pretty standard.
On this specific 8-inch disk, it will reach absolute maximum capacity when you save exactly 16 of those files. So the disk holds 16 files total.
Okay.
If you are using a one-sector allocation unit, you are wasting, on average, half a sector per file due to internal fragmentation. That is 64 bytes of internal waste per file. 16 files multiplied by 64 bytes equals exactly 1,024 bytes of total wasted space across the entire physical disk.
Wait, hold on. Let me process that.
Look at the numbers.
You are telling me that if you use a one-sector allocation unit, you only waste 1,024 bytes to internal fragmentation. But to achieve that efficiency, you are forced to spend thousands and thousands of bytes just to store the massive, bloated FAT table required to track it all.
You have hit the exact mathematically paradoxical wall that Paterson hit.
The map becomes larger than the territory.
The map becomes significantly larger and more cumbersome than the territory it is attempting to optimize. It is a massive, cascading negative return on investment. You spend 48 sectors of structural overhead just to save a hypothetical 8 sectors of fragmented waste.
The mathematical reality simply does not justify the granular approach.
It doesn't. That is a phenomenal aha moment. The intuition to make the unit smaller is completely correct in isolation, but catastrophic when applied to the systemic overhead. So they were backed into a corner and forced to compromise.
They were. MS-DOS intentionally chose to use 4 sectors per allocation unit for this specific 8-inch disk format. Yes, it drastically increases the potential internal fragmentation waste at the end of every file.
But in exchange,
it drastically shrinks the total number of allocation units on the disk from 2,000 down to 500, which subsequently shrinks the size of the file allocation table on the disk by a massive margin.
it is a cold, calculated mathematical trade-off. You willingly accept throwing away hundreds of bytes of wasted space at the end of your files simply to keep your structural overhead manageable.
And keeping that FAT array as physically small as possible was absolutely critical for an even bigger, much more radical architectural reason.
The FET in RAM decision.
Yes.
This is without a doubt where Tim Paterson placed his boldest engineering bet.
Sure.
MS-DOS was designed to read the entire file allocation table off the disk at boot time and keep the entire map permanently cached in main memory at all times.
Which, frankly, sounds completely insane given the context we established earlier.
It sounds crazy.
We just spent 10 minutes talking about how unbelievably precious RAM was.
Hmm.
They were literally designing the command processor to overwrite its own user interface just to save 5 kilobytes of memory for applications.
Yeah, the transient split.
And yet, simultaneously, they make the decision to permanently dedicate a substantial chunk of that exact same precious memory to hold a complete map of the disk drive. It seems like a massive contradiction. Why burn the RAM?
They burn the RAM for one specific, highly prized metric: blazing fast, random access speed.
Speed over everything.
Let's visualize the alternative. If the FAT is stored exclusively on the physical disk and an application wants to jump to a specific record in the middle of a massive file, the OS is forced into a terrible mechanical loop.
It has to go to the disk,
First, it has to physically move the heavy drive head to the track containing the FAT. It reads the FAT sector from the disk just to find out the physical location of the data. Then it has to physically move the drive head again, stepping all the way across the platter to the track where the actual data lives to perform the read.
Physical mechanical disk seeks are, by orders of magnitude, the slowest, most agonizing operation in all of computing.
By paying the exorbitant cost to keep the entire map permanently cached in solid-state RAM, the OS can mathematically calculate exactly where any piece of data is instantly, using CPU cycles, with absolutely zero physical mechanical movement.
If we want to connect this to modern AI architectures, this is the exact same trade-off we see with large language models and the KV cache.
Oh, that's a good comparison.
AI researchers will gladly sacrifice massive amounts of incredibly expensive GPU VRAM just to cache the attention states of previous tokens. They are willingly hoarding memory because recalculating those states from scratch every single time, the equivalent of seeking the disk, is computationally paralyzing.
In MS-DOS, the source text explicitly notes that in a real-world application, like a database inquiry, where a user is constantly jumping around doing random reads, this single AFIT in RAM caching decision made MS-DOS twice as fast as competing systems like CP/M or early Unix implementations.
2 times the performance throughput, achieved purely by hoarding the map in RAM.
It is the classic systems trade-off. You sacrifice precious memory capacity to secure a massive structural leap in I/O speed.
Let's actually pull back the curtain and look at how that map in RAM mechanically functions. We're going to do a step-by-step walkthrough of the internal logic. Think of this as Demo 1, the FAT scavenger hunt.
If a file is completely fragmented, with its pieces scattered across 20 different physical locations on the disk, how does the OS actually scavenge all those pieces and reassemble them without losing its mind?
Okay, let's trace the exact execution path. An application asks to open a specific file. Step 1. MS-DOS intercepts the request and looks at the 32-byte directory entry we discussed earlier.
Right, the metadata.
Inside that metadata, it finds the starting pointer. The pointer says the very first allocation unit of this file is located at unit 5. So MS-DOS immediately knows where the first chunk of data resides.
But the file is massive. How does it find the second chunk?
Step 2. The OS does not query the disk. It goes directly to the FAT array sitting in RAM. It treats this array as a simple one-dimensional list of integers. It looks specifically at index slot number 5.
Then what does it find?
The value stored inside index slot 5 is the integer 6. This single integer tells the OS 2 distinct pieces of information instantly. First, the file's data continues linearly in physical unit 6, and second, your next stop on the scavenger hunt map is index slot 6.
Step 3. It jumps down the array to index slot 6. It reads the value. The value there is 3, so the system knows the file has become fragmented. It physically jumps backward on the disk to unit 3.
Then it also looks at index slot 3 in the map. The value stored in slot 3 is 9.
Step 4. Following the breadcrumbs, it jumps to index slot 9 in the array. The value sitting there is 10.
Step 5. It jumps to index slot 10. And inside slot 10, it finds a highly specific reserve control value, a -1.
-4.
This is the master end-of-file marker. It signals to the OS, halt execution, stop reading. There are no more allocated units for this file.
So simply by bouncing through an integer array in solid-state memory, MS-DOS can instantly map out that the file physically occupies units 5, 6, 3, 9, and 10 in the exact chronological order without spinning the diskhead once.
And what if the application decides to append data and extend that file?
The logic is beautifully simple. The OS just rapidly scans the FAT array in RAM, looking for any index slot holding a 0. A 0 is the universal flag for unallocated free space.
Let's say it scans and finds that index 27 holds a 0.
The OS navigates back to index 10, the old end of the file, and overwrites the -1 marker with the number 27. It then navigates to index 27, injects a -1 there to establish the new end-of-file boundary, and it is done.
You have just seamlessly extended a highly fragmented file in milliseconds, regardless of where that new sector physically lives on the magnetic platter.
It is an incredibly elegant linked list, implemented entirely within a flat one-dimensional array. But we need to get into the absolute weeds of how that array is structurally packed into RAM, because this brings us to Demo 2. Bit shifting, the 1.5-byte FAT entry.
You casually mentioned earlier that the architectural math requires exactly 1.5 bytes for every single FAT entry. That exceeds to exactly 12 bits per entry.
Yes. And from a pure software engineering standpoint, this is an absolute nightmare to program, but it is fundamentally brilliant for conserving memory.
We need to explain why 12 bits was the magic number.
If they had designed the FAT using a standard 8-bit entry, which is 1 byte, the maximum number of allocation units they could track would be 2 to the power of 8, which is only 256 units.
That is nowhere near enough granularity to map an entire 8-inch disk.
If they jumped up to a standard 16-bit entry, which is 2 bytes, they could track 65,536 units. That is massive overkill for an 8-inch floppy disk, and it guarantees that you are wasting an entire half byte of memory for every single entry in the table.
So Paterson settled on 12 bits. 2 to the power of 12 gives you exactly 4,096 possible allocation units. That number was the absolute perfect sweet spot to map the disk while minimizing the RAM footprint.
But hold on, I have to push back on this because hardware CPUs absolutely despise unaligned memory access.
Oh, they hate it.
Processors do not read data in 1.5 byte chunks. The 8086 processor reads standard 8-bit bytes or standard 16-bit words. You literally cannot write an assembly instruction asking the CPU to fetch exactly 12 bits from memory.
You just can't do it.
So you are telling me they intentionally misalign their core data structures, forcing the CPU to perform complex, cycle-burning, bitwise mathematics on every single disk read, just to shave a tiny fraction of a kilobyte off the total memory footprint.
That sounds like a profound performance bottleneck.
How did Paterson actually pack these entries together so that 2 discrete 12-bit entries fit perfectly into 3 standard 8-bit bytes?
You are exactly right about the CPU constraints, and this is where we descend into raw, brutal, bitwise operations. The math to unpack it is exhausting, but necessary. Let's walk through the exact, literal assembly logic required to read the map.
Let's do it.
Suppose the operating system needs to read the data for entry number n from the FAT array. The very first programmatic step is to multiply your index n by 1.5. If the result is a fraction, you use integer truncation to drop the decimal.
The resulting integer gives you the exact physical byte offset in the FAT memory array where your requested data sequence begins.
Okay, I am visualizing the array. We have the byte offset.
Next, you instruct the CPU to fetch a full 16-bit word starting at that exact byte location. But remember the problem. You have just fetched 16 bits of data into the CPU register, but your logical entry is only 12 bits long. You have 4 extra garbage bits.
Which 12 bits do you isolate and keep?
That answer depends entirely on a mathematical condition. Was your original requested index n an odd number or an even number?
Because the 12-bit entries are packed together like overlapping, staggered puzzle pieces.
Precisely. They are staggered across the byte boundaries. If your original index n was an odd number, which implies that you had to truncate a 0.5 decimal during the multiplication step, your specific 12 bits of data are sitting entirely in the top, most significant portion of the 16-bit word you fetched.
So to isolate them, you take that 16-bit word in the register and execute a logical right-shift operation by exactly 4 bits.
You literally shove the binary bits to the right, pushing the bottom 4 garbage bits off the edge into oblivion, and what you are left with, perfectly aligned in the register, is your pristine 12-bit integer.
And what is the execution path if the original index was an even number?
If the index was even, it means your 12 bits of data are sitting entirely in the bottom, least significant portion of the 16-bit word. So instead of shifting the data, you apply a bitwise AND mask.
You lay a binary mask over the register that preserves the bottom 12 bits and forcefully zeroes out the top 4 garbage bits.
It is frankly exhausting just to describe it, let alone program it in assembly language without a modern debugger.
They're forcing the processor to perform integer multiplication, floating point truncation logic, 16-bit unaligned memory fetches, conditional branching, and bitwise shifting or masking for every single solitary read of the file allocation table.
It perfectly and undeniably illustrates the brutal lengths they were forced to go to. RAM was so unbelievably expensive and constrained that intentionally burning hundreds of precious CPU cycles on complex bitwise gymnastics was actually considered the superior preferred engineering trade-off.
And speaking of exhausting math, let's move to Demo 3, the translation engine. This is where we finally see how MS-DOS SYS, our head chef in the restaurant analogy, takes a completely abstract high-level application request and mathematically grinds it down into absolute physical reality for the disk drive.
Let's walk through the exact mathematical sequence laid out in the architectural text.
Okay, set the scene. Imagine I'm a developer writing a primitive database application.
You are the application program. You have absolutely no concept of physical sectors, allocation units, or disk drives. You simply treat your data file as a continuous abstract series of logical records.
Let's say I, the programmer, define a single record as being exactly 80 bytes long.
And your application wants to read 15 of these records at a single time to process them. You have already read the first 15 records, and now you send a generic system call to MS-DOS. Please read the next 15 records from this file, starting precisely at record number 15.
So the parameters are 80 byte records. We want to start at record index 15, and we want to retrieve 15 of them in total.
Right. MS-DOS intercepts that string of parameters and instantly converts it into a raw, byte-level mathematical operation. First, it must calculate the exact starting byte position within the file. 80 bytes per record multiplied by the starting record index of 15 equals 1200.
So the OS knows it needs to begin reading at exactly byte offset number 1200 within the file's data stream.
Next, it calculates the total payload size. 80 bytes per record multiplied by 15 requested records equals a total data transfer of 1200 bytes.
Exactly. Now, MS-DOS has to map that abstract byte offset to the physical architecture of the disk. The physical sectors on our specific floppy disk are hard-coded to 128 bytes each.
So we take our starting byte position, 1200, and we divide it by 128.
If you do the long division, 1200 divided by 128 is 9, with a remainder of exactly 48.
That quotient and remainder represent our exact coordinate on the disk abstraction. It dictates that we need to start reading at logical sector index 9 of the file, and specifically, we need to skip the first 48 bytes of that sector and begin extracting data at byte 48.
But we're still operating in the realm of logical abstraction. We still don't know where sector 9 actually physically resides on the magnetic media. We have to map that logical sector back to a physical allocation unit.
Right. The OS checks the parameters and knows that for this disk, allocation units are composed of 4 sectors each. So we take our logical sector index 9 and we divide it by 4. The result is 2 with a remainder of 1.
What this specific math means in plain physical English is that the OS needs to navigate to the third allocation unit of the file because we always start counting arrays at 0.
And then read the second physical sector contained within that specific unit.
So MS-DOS takes that calculation, jumps into the 12-bit packed FET array residing in RAM, utilizes the scavenger hunt methodology we just discussed to traverse the linked list, and discovers the physical location of the third allocation unit on the disk.
Let's say the FAT maps it to physical sector 35 on the disk plotter. The OS commands the IOSYS plumbing to read sector 35, extract the payload starting precisely at byte 48, and hand it back up to the database application.
But here's where a highly sophisticated optimization kicks in. MS-DOS does not just blindly read one single sector, hand it off, and then recalculate the next one.
Once it calculates the starting position, it actively looks ahead in the file allocation table. It runs a check to see if the required sequence of allocation units happen to be physically contiguous on the disk surface.
If it sees that the next 15 records are laid out perfectly end-to-end, it batches them together into a single, massive, continuous, multiple-sector I/O request.
It bypasses the piecemeal approach entirely. It talks directly to the IOSYS layer and says, look, I have calculated that I need physical units 9 and 10, and the FAT confirms they are sitting right next to each other on the track. Do not turn the drive head off. Do not stop the rotation. Just open the buffer and vacuum up all 8 physical sectors in one continuous, uninterrupted magnetic read.
Exactly. It aggressively minimizes the overhead of constantly pinging the hardware controller. It allows the physical mechanical drive to actually reach and sustain its maximum rotational throughput.
This is the exact reason why early MS-DOS disks rarely required physical sector interleaving. If you have a smart mathematical OS kernel that can intelligently batch consecutive reads, you want your sectors laid out sequentially on the physical tracks to achieve maximum velocity.
But as mathematically brilliant as all this dynamic mapping, 12-bit packing, and read-ahead batching is, we have to pause and do a severe reality check. Because this highly constrained architecture harbored some catastrophic fundamental limits, particularly when it encountered specific operational edge cases.
And the most glaring, painfully obvious failure point in the entire system was the sector buffer mechanism.
This brings us to Section 6 of the architecture text, the single-sector buffer bottleneck. In a desperate, overarching bid to save every last possible drop of precious memory, the early versions of MS-DOS relied on just one internal sector buffer.
One single chunk of RAM dedicated to holding data in transit.
Let's explain what that constraint actually dictates in practical, real-world operations. Let's say your database application wants to write a massive file sequentially, but it's programmed to write the data in tiny incremental chunks, say 16 bytes at a time.
MS-DOS is smart enough to know that it shouldn't instantly spin up the disk drive and execute a physical write for every 16-byte chunk. That would destroy the drive and take hours.
Instead, it utilizes a standard technique called delayed writing. It takes those 16 bytes and quietly copies them into the single 128-byte internal sector buffer in RAM.
When the database application issues the command to write the next 16 bytes, MS-DOS simply appends them to the end of the data already sitting in the buffer. It patiently waits, accumulating data until the application has executed enough write commands to completely fill the 128-byte buffer to the brim.
Only at that exact moment does it actually engage the drive motor and flush the fully packed sector to the physical magnetic disk. When operating linearly, it is a highly efficient mechanism.
It is incredibly efficient, right up until you hit a multiplexed context-switching edge case. Because, as we established, there is only one buffer. If you are trying to do two things at once, the system collapses.
Let's examine the ultimate failure mode for this architecture.
Crashing.
To visualize this, think of a chef in a kitchen who only owns a single mixing bowl.
A single mixing bowl.
If they're trying to bake a chocolate cake and toss a Caesar salad at the exact same time, they are forced to completely wash and dry the single bowl out between handling every single ingredient.
In the computing world, the classic example of this is running a compiler. A compiler's entire job is to read a tiny fragment of source code from an input file, process it into machine code, and immediately write a tiny fragment of compiled code out to a separate output file.
Let's follow the exact agonizing sequence of physical disk transfers for that compiler scenario, assuming both the input and output files are utilizing tiny 16-byte records. First, the compiler asks the OS to read 16 bytes from the source code input file.
MS-DOS spins up the drive, reads the correct physical sector from the input file into the single sector buffer in RAM, extracts the 16 bytes, and hands them to the compiler.
The compiler takes a few milliseconds to process those bytes, translates them into machine code, and then immediately asks the OS to write 16 bytes of output to the destination file.
And this is exactly where the entire architectural house of cards completely falls apart. MS-DOS only possesses one single sector buffer, and that buffer is currently occupied, holding the sector from the input file.
It is forced to discard that input data.
It must spin up the drive, read the appropriate physical sector for the output file off the disk and into the buffer just to prep it, insert the new 16 bytes of compiled code into the buffer, and then flag the buffer as dirty, meaning it contains new data that eventually needs to be flushed to the disk.
But wait, before it even has a chance to flush it to the disk, the compiler loops back around and asks for the very next 16 bytes from the input source file.
Exactly. And the single buffer is now holding the dirty output file data. It cannot just discard it. So MS-DOS is forced to execute a physical write of the dirty output buffer to the magnetic disk, and then it is immediately forced to execute a physical read of the input file sector back into the single buffer all over again.
For every single tiny microscopic pair of 16-byte read-write operations, the operating system is forced to execute 3 complete, slow mechanical disk transfers. Read the input sector, read the output sector to prep the buffer, write to the output sector to save the data.
Over and over and over again, thousands of times a minute, the single memory buffer is just violently overwriting itself in a constant loop.
The performance degradation is unbearable. It slows the entire computer system down to an absolute agonizing crawl. If you listen to the machine, the hard drive head is just thrashing violently back and forth across the disk tracks, literally grinding its mechanical gears to death, desperately trying to juggle the state of 2 separate files, utilizing one tiny 128-byte sliver of memory.
And in the source text, Tim Paterson is remarkably transparent about this. He explicitly calls this bottleneck out. He freely admits that this is a systemic design inadequacy that is very difficult to defend from a pure computer science perspective, except for the absolute overriding fact that it kept the memory footprint of the operating system exquisitely small.
The OS simply could not afford the RAM to provide a second buffer.
The only viable solution in the early 1980s was for third-party application developers to recognize that this massive OS-level bottleneck existed and proactively engineer their way around it. If you were writing a professional compiler, you could not rely on the OS. You had to manually pull massive multi-kilobyte chunks of input data into your own application's internal memory arrays to completely bypass MS-DOS and avoid thrashing the single OS buffer.
Which naturally brings us to the inevitable evolution of the system and the massive philosophical controversy surrounding the release of MS-DOS version 2.0.
Because by the time MS-DOS 2.0 rolled out of Microsoft in 1983, the fundamental hardware landscape of the industry was undergoing a seismic shift.
We were moving away from flimsy 160 kilobyte floppy disks, and the era of the massive, heavy Winchester hard disk was becoming a commercial reality.
MS-DOS 2.0 was forced to introduce some absolutely essential, non-negotiable architectural features to handle this new hardware. Most notably, it brought in hierarchical subdirectories, the nested tree structure of folders we still use today.
A flat directory containing hundreds of files is impossible to manage on a 10 megabyte hard disk.
And critically, to fix the exact problem we just discussed, 2.0 finally introduced multiple configurable sector buffers. A user could alter a configuration file at boot time to allocate 10 or 20 sector buffers in RAM, permanently resolving the compiler thrashing issue.
But in the process of adding those essential features and buffers, the Microsoft engineering team made a fundamental, irreversible architectural change that Tim Paterson vehemently, explicitly disagreed with.
They abandoned his core philosophy.
They stopped keeping the entire file allocation table cached in main memory.
Right. Microsoft recognized that as hard drives grew exponentially larger, the FAT required to map them would also grow exponentially larger. A 10 megabyte drive requires a massive FAT.
So they moved the FAT out of dedicated RAM and began treating the map just like any other piece of standard disk data. They paged it into the new disk buffers only when needed.
It meant that only tiny, fragmented pieces of that FAT were actually residing in fast RAM at any given millisecond.
And Patterson's critique of this decision in the source text is razor sharp. His entire logical argument was rooted in projecting hardware cost trends. He argued aggressively that the physical manufacturing cost of RAM was dropping every single day.
Dedicating a few extra kilobytes or even a few dozen kilobytes of RAM to hold the entire massive FAT table should have been viewed as a completely painless, obvious trade-off by the time 2.0 was released, given the sheer performance benefits it yielded.
By forcing the FAT out of solid-state memory, Microsoft forced the operating system to revert back to executing slow, physical mechanical disk reads simply to find out where the requested data was hidden.
Paterson points out the exact performance penalty. If an application is performing random access inquiries on a highly fragmented database file stored on a Winchester hard disk, the operating system might be forced to physically seek to several different, wildly separated sectors of the FAT on the disk in random order, just to trace the linked list and find the allocation unit.
It completely destroys the blazing fast, zero-latency, random access performance that was the defining hallmark of his original memory hoarding design.
It is a genuinely fascinating, highly respectful disagreement over architectural philosophy, and it highlights the hardest part of systems design. Paterson is looking at the rapidly dropping price curve of silicon RAM and arguing, scale the memory up, keep the map in RAM, prioritize the speed.
Microsoft is looking at the rapidly exploding capacity of mechanical hard drives, where the FAT table itself would eventually consume all available system RAM, and arguing, we cannot afford to dedicate that percentage of RAM to metadata anymore. We have to page it, even if it hurts I/O performance.
They were both entirely logically correct, but they were optimizing for different constraints on the timeline of hardware evolution.
Which leads us perfectly into our final synthesized takeaways for this deep dive. We have covered a tremendous amount of extremely low-level 1980s bare metal engineering. What can modern developers, working with cloud infrastructure and gigabytes of RAM, actually extract and apply from this architecture?
I think takeaway one is paramount. Abstract the messy hardware at all costs. This is the absolute genius of the logical sector array.
By intentionally hiding the chaotic, physical reality of spinning tracks, drive motors, and mechanical heads behind a clean, pristine, flat mathematical interface, MS-DOS allowed independent developers to build highly complex file systems that did not instantly shatter the moment a hardware vendor invented a new brand of floppy disk.
If you are building an API, a cloud platform, or a microservice today, your primary overriding job is to completely hide the mechanical complexity of your backend from the end user. Give them logical sectors to interact with, never physical tracks.
Takeaway 2. You must understand internal versus external constraints, and you must ruthlessly optimize for the specific bottleneck that is hurting you the most, even if it forces you to create massive waste elsewhere in the system.
Right. MS-DOS actively, mathematically chose to accept the penalty of internal fragmentation. They were perfectly willing to literally throw away hundreds of bytes of storage space at the end of every single file on the disk, simply to drastically shrink the overall size of the file allocation table.
They willingly wasted cheap disk space to aggressively protect their most precious, constrained resource, RAM overhead. As an engineer, you have to definitively know what your most expensive resource is, whether that is compute, memory, or network bandwidth, and you have protect it, even if your solution looks incredibly inefficient or wasteful on a raw spreadsheet.
Takeaway 3. State matters deeply in buffer management. The single-sector buffer architecture in early MS-DOS is a painful masterclass in how a design choice that appears highly efficient for sequential operations becomes utterly catastrophic the moment you introduce context switching.
The thrashing compiler example proves that you cannot treat I/O as a black box. You must deeply, intimately understand exactly how your underlying operating system or cloud environment batches its I/O requests.
If your execution environment utilizes a highly constrained single buffer pipeline, you absolutely cannot rely on it to seamlessly handle multiplexed asynchronous tasks. You are forced to lift that state management directly into your own application logic, or your performance will completely collapse under the weight of context switching.
And finally, takeaway 4. Memory versus I/O trade-offs are never static. They are constantly evolving beneath your feet.
Tim Paterson's philosophical critique of MS-DOS 2.0 perfectly illustrates this reality. His aggressive decision to permanently store the fat in RAM made absolute undeniable sense on day one, when floppy disks were tiny and random access speed was critical.
But as hardware rapidly scaled up to massive Winchester hard disks, that exact same brilliant design decision transformed into a major architectural liability and a battleground. An architectural choice that represents the pinnacle of optimization today might become your most crippling technical debt tomorrow, simply because the hardware reality shifted while you weren't looking.
Which leaves us with a provocative thought to mull over as we wrap up. When we look at modern enterprise systems, we are rapidly moving toward hardware architectures equipped with literally terabytes of RAM and massive, lightning-fast, solid-state NVMe storage arrays.
With resources at that scale, have we essentially circled all the way back around to Tim Paterson's original 1980 philosophy?
With memory becoming this vast and relatively cheap, should we stop relying so heavily on complex, overhead-heavy paging algorithms and go back to simply loading massive multi-gigabyte index structures and databases entirely into main memory to achieve absolute zero latency random access?
It is a question that forces you to completely rethink the foundations of how we structure and retrieve data in modern distributed databases. The constraints change, but the mathematical trade-offs are eternal.
Find your weirdest edge case and share it. We love this stuff. Tell us what to cover next. Leave a comment and rating. Subscribe if you enjoyed. Thanks for listening. Until next time.